this session. So this is by Frits Verhagen, and he's going to talk about conditions for large sample majorization of pairs of flat states in terms of the alpha Z relative entropies. The stage is yours.
Thank you. I'm going to talk about this project that is a joint work with Marco Toma Miguel and RKH Passelo. So as you see, the title contains three terms: majorization, flat states, and relative entropy. So first I will discuss those three things, and then I'll get to the results as soon as possible. So first, majorization. So we consider two pairs of quantum states, rho sigma, rho prime sigma, and we say that the one pair majorizes the other if we can find a quantum channel such that rho is sent to rho prime and sigma is sent to sigma prime. And then large sample majorization is if for n large enough we can find a quantum channel such that n copies of rho get sent to n copies of rho prime, and the same for sigma and sigma prime. For catalytic majorization, we require that there is a so-called catalyzer pair, tau phi, and a channel C such that rho tensored with tau is sent to rho prime tensored with tau, and similarly sigma and phi are sent to sigma prime and phi. We can also look at the asymptotic or approximate setting. So here we don't require the target states to be reached exactly, but the target state rho prime is only reached approximately, but with vanishing error. So we say for every epsilon greater than 0, we have a state rho prime epsilon that is very close to rho prime in terms of the fidelity between them, such that rho sigma majorizes rho prime epsilon sigma prime in the large sample setting. And we could do a similar thing for asymptotic catalytic majorization. And in this case, also the catalyst pair is going to depend on epsilon. Okay, now we can get to the results. But first, I want to make clear what we mean with the relative entropy. So relative entropy is just a map from pairs of states to the real numbers that satisfies additivity in terms of the tensor product and the data processing inequality. So we can write it like this with our majorization definition. Now the goal of this work is actually to identify a set of relative entropies D such that when we have two pairs of states and all the relative entropies in this family D are ordered like this, so always the relative entropy evaluated on the input pair is always bigger than or equal to that evaluated on the output pair, then this is the case if and only if the input pair majorizes the output pair, either in the large sample or catalytic setting, either asymptotically or exactly. So this is kind of, we're hoping for a result like this. And the reason that you could hope for a result like this is what kind of reminds us of the second law of thermodynamics, maybe, and also the converse direction is very simple. It follows immediately from additivity and DPI. But of course, the direct implication is much harder. Okay, so it's not an easy task to identify a relative entropy for a general pair of quantum states. In the classical case, all relative entropies on two probability distributions are known. It's just the Renner divergences. But for any fixed alpha Renner divergence, there are multiple quantum generalizations or extensions of that, and we're not sure we don't know all of them, and it's hard to prove whether you know all of them or not. So okay, we will restrict. We will not consider all possible quantum states, but we'll restrict to a certain setting. Namely, we will look at CQ states, so classical quantum states. So we look at pairs rho sigma where we have a classical register, that is, these flags I are from the classical register, and then we have these component quantum states rho I and sigma I. But we're going to further restrict this to the case that rho I and sigma I are actually pure states. And for technical reasons, we're also going to require that the states are not completely orthogonal to each other. So there is an I where this inner product is not equal to 0. And so all such pairs we will denote by this calligraphic F. I also need to introduce this definition of rho sigma not being parallel, which means that there is an I for which the inner product of alpha I and beta I has a modulus that is strictly less than 1. So if the modulus would be equal to 1, that means that it's kind of like a classical component, because the pure states are parallel. So in a sense, non-parallel means that the whole state only has quantum components. Okay. Yeah, so we were looking at these types of pairs of states, rho sigma, and it has an interesting subset of states. So a flat state is a state which has only one eigenvalue that can be repeated multiple times, and which means that it can be written as a projection, normalized, of course, normalized projection as such. And then there's a very useful result called Jordan's lemma, which says that if you have two projections, you can simultaneously block diagonalize it into blocks that have dimension at most 2, and the blocks have rank at most 1. So after block diagonalizing, it would look, rho and sigma would look something like this, where you can have a one-dimensional block, which is basically like a classical component, or you can have a two-dimensional block, and furthermore, this two-dimensional block represents a pure state because it has rank at most 1. So that's very useful. So these pairs of flat states are actually a subset of of the states that we consider. Yes, so it will turn out that the relative entropies that are applicable, or that apply to the setting of majorization for these pairs of states, are the alpha z relative entropies. This is their formula for general states rho and sigma. You also have to take certain limits if alpha goes to 1 and z is 0, but I won't get into those details. So this is nice because it recovers some known relative entropies. If we set alpha equal to z, then we recover the sandwiched relative entropy, and for z is equal to 1, you get the pets. Yeah, this was introduced by Jakschik and others, and also Oudenaarde and Datta. There were a number of papers that tried to prove what the exact region of alpha and z was where DPI holds. And the last paper on that subject was by Zhang, who proved what the exact parameter range is where DPI holds. And you can see that in this picture. So for the green and this green area R, and also this more grayish-green area, those are exactly the regions where DPI holds. And it will turn out that in our case, we can characterize large sample majorization in terms of this subset R of specific divergences. Yeah, so now I'm ready to state the first result on asymptotic majorization. So we take two pairs, rho sigma, rho prime, sigma prime. We assume that rho and sigma are non-parallel, and that furthermore rho prime and sigma prime do not commute. Then we have the following three statements. So the first statement is that we have the ordering of the alpha z relative entropies for this parameter range that we consider. Second statement is that we get asymptotic catalytic majorization. And the third statement is that we have asymptotic large sample majorization. So statements 1 and 2 are always equivalent. And if we additionally require this additional assumption that there is some I for which the pure states are basically perpendicular, then all three of these statements are equivalent. Okay. So, okay, to present the next result, I have to introduce a slight modification of the alpha z relative entropies. So we consider this set D of the alpha z relative entropies multiplied with this particular prefactor. Now, but this prefactor, so now using this, because of this prefactor, we can take limits for alpha going to 0 and 1, and alpha going to, oh sorry, this alpha should be a z. So we take the limit of alpha goes to 0 and 1 for fixed z, and we take the limit of z goes to infinity for fixed alpha. And in that way, we get like extra relative entropies. And if we add those to the set D, we get a compact set, compact in the topology of pointwise convergence, this set D bar. And this is an illustration of D bar. So basically, you have all the relative entropies in this region, and this this point here at z is infinity represents the unique extra relative entropy that you get in the limit z goes to infinity, because that does not depend on the alpha, it's independent of the alpha. Okay. So, okay, now, so this is the theorem on exact majorization. In this case, we require that the pairs are basically strictly ordered. This is a strict inequality for all the relative entropies in d bar, so also including the limit points that I just discussed. And in that case, we know that the input rho prime sigma will majorize rho prime sigma prime in the exact catalytic setting. And again, if we require that there are two pure states that are orthogonal to each other, then we also have the exact large sample majorization. So in the other direction, if we either have catalytic or large sample majorization, then we know, actually, yeah, by data processing and additivity, that this inequality will hold, but then not strictly. Okay, so our results actually allow us to write down the rate at which we can convert one pair into another pair. So what I mean by a rate is, I will define it. So we first define this achievable conversion rate, which is a real number r, and basically such that for n large enough, you are able to convert your input state to your input pair to your output pair at a rate that is at least as big as r. And then the optimal conversion rate will be the supremum of all such achievable rates. Then the result is that, well, if we have two pairs, we have to assume that the input pair is non-parallel and also satisfies this condition. Then the optimal conversion rate is given by the infimum of the ratio of the alpha z divergence of the input pair divided by the alpha z divergence of the output pair. Okay, so those are the results, and now I want to say something about the methods that we use. Basically, our methods are some real algebraic techniques using preordered semirings developed by Tobias Frits. He calls it the Vergleichsstellungssätze, which basically is German for something like theorems on like points. Points that can be compared to each other, or something like that. So, so the points are, in our case, are these pairs of states, and the comparison is that they are that the relative entropies are ordered in such a way. So these theorems, they give sufficient and, well, almost necessary conditions for exact large sample and catalytic majorization in terms of certain monotones, and these monotones, they will turn out to be the alpha z relative entropies. Okay. Let me quickly define what a preordered semiring is. So it's just a set with an addition and a multiplication and a preorder, such that, well, these very, well, natural conditions are met. So basically, it's everything that you expect, except that the addition is not, does not have to have an inverse in general. That's what makes it a semiring. So an example of a preordered semiring, very easy one, is R+. So we consider all non-negative real numbers with the regular addition and multiplication and regular preorder. We can also consider the tropical reals, as they're called, TR+, which are also the non-negative real numbers with the normal multiplication and ordering. But now the addition is given by x plus y is the maximum of x plus y. Then we can consider homomorphisms on this semiring to one of these two special semirings, R+, or the tropical TR+. That preserves the semiring structure, so it's a homomorphism. And it's also monotone in the sense that if x is greater than y, then phi of x should be greater than phi of y. So it's non-decreasing, or it could be non-increasing with the inequality the other way around here. A degenerate homomorphism is a homomorphism where if for any elements that are any two elements that are comparable, so x is less than y, then also phi evaluates to the same value for x and y. Such a homomorphism is called degenerate. And in that case, we can define a derivation of a degenerate homomorphism. So derivation is a function from the semi-ring to the real numbers that satisfies some Leibniz rule, which reminds us of the product rule in taking a derivative. And it's also monotone. And then I present here like an informal version of the Vergleichsstandard Satz. There are some extra conditions that I don't want to get into. Extra conditions on S, the semi-ring. So if you have a semi-ring S, you fix two elements X and Y. If you have strict ordering in the homomorphisms, and you also have strict ordering in the derivations, then you have basically large sample majorization, so x to the power n is bigger than y to the power n, and also there's a c in S, which is the catalyst, such that c times x is bigger than c times y. And if 2 or 3 is satisfied, then by the additivity properties and the monotonicity, 1 and 2, so these inequalities will also be satisfied, but then non-strictly. So yeah, this is basically the theorem that we will use to derive our results. But first, we have to define the semi-ring that we actually use. So our semi-ring consists of pairs of this form. So we have A and B are both self-adjoint matrices on some finite dimensional Hilbert space that we can decompose into components HI, such that A and B can both be decomposed as a direct sum as such. So here the PI and the QI are non-negative numbers, but they don't have to add up to 1. So semi-ring is a bit bigger than just quantum states, and the quantum states will be those elements where A and B have trace 1. And alpha I and beta I are normalized vectors in the same Hilbert space HI. For technical reasons, we also have to require that they're not completely orthogonal. And let's denote all those pairs by V. Addition is defined like this, so it's just component-wise addition by using the direct sum. And multiplication is similar, so just component-wise multiplication by the tensor product. And the preorder is defined by requiring that there is a quantum channel that takes like this bigger pair that's considered bigger to the pair that's considered smaller, like this. So, but this is still not a semi-ring because the addition and the multiplication is not commutative in this case. So we have to define an equivalence relation to get rid of that problem. So basically we say that if you have two pairs, A, B, and A prime, B prime, we say that they are equivalent to each other if you can obtain one from the other by permuting the component Hilbert spaces HI, or by adding or removing copies of just 2 zeros, or if they are, or if the component spaces of the component spaces of these pairs are basically equivalent up to some isometries. And then if we consider all the equivalence classes, and we call this S, then it turns out that this is a semi-ring with the induced addition, multiplication, and preorder. So, so the collection F I previously defined, the pairs of states that we consider are basically just the normalized pairs in the semi-ring. And now the task is to identify all the monotone homomorphisms and derivations in S. That is most of the work. But first, I just want to give an idea of why the quantum relative entropies are so difficult, actually. So if you have any pair in our semi-ring, and say you are able to decompose it as such, so AB is a direct sum of like smaller elements, AI and BI, then because of the additivity of a homomorphism, the homomorphism evaluated on this pair AB is just the sum of the homomorphism evaluated on the smaller blocks AI, BI. So if somehow you can bound the size of AI and BI, that would help, because then that means that to figure out what a homomorphism evaluates to, you just have to look at the smaller blocks of fixed size. And well, for flat state pairs, we know that Jordan's lemma already tells us that these blocks will be at most dimension 2. So that is actually what allows us to actually compute all the homomorphisms in this special case. Okay, so yeah, I want to give an idea of basically a proof sketch of how the z exponent appears. So I mean the z exponent in the alpha z relative entropy. So as we saw in the previous slide, we only have to compute phi evaluated on a pair of pure states. And according to the equivalence relation I defined, if you have any pair of pure states, alpha, beta, you can find unitaries that transform it into this pair of density matrices. And as you can see, it only depends on this angle theta. And basically, the angle theta is related to the fidelity between the two pure states. It's the fidelity is equal to the cosine squared of this angle. And this allows us to define this function lowercase phi. We define phi x to just be uppercase phi evaluated on any pure state pairs that has this fidelity equal to x. And it's easy to show that phi is multiplicative. And then there's this nice result, Cauchy's functional equation, that if phi furthermore satisfies some regularity condition, then phi x has to be of this simple form. So phi x has to be x to some power z. And this z is the z in the alpha z relative entropy. So that's where it appears. I still have some time. Yes, so okay, so these were the pairs that we were considering. Now, if you actually insert these in the alpha z relative entropies, you will see that that this is the formula that you will get for these specific quantum states, and then you get this this special relative entropy for z going to infinity. So actually, this can be seen as kind of a generalization of two previous known results. The first one is one by Ullmann, already from 1985. So he proved that if you have two pairs of pure states, you can convert one pair to another pair if and only if the fidelity of the input pair is less than or equal to the fidelity of the output pair. And in some previous work that we did, we were basically considering a similar setting, but we had semi-rings where these pairs AB are classical, so basically they are diagonal. And in that case, the homomorphisms turned out to look like this. And these basically give rise to the Renner divergences, the classical ones. And then these two special homomorphisms, which are related to the D0 Renner divergence. And these two results are also needed in our proof for, well, basically proving that we get these homomorphisms. Some final remarks. So we were considering states of this form, CQ states with pure components. We found conditions for large sample and catalytic majorization, both asymptotically and exactly. And it turned out that these terms can be given in, these conditions can be given in terms of the alpha z relative entropies for this specific range of parameters where it is where the DPI holds. And also the optimal rate of conversion of two such pairs is given by this nice expression. And we believe that this is the first operational interpretation of the alpha z relative entropies. Some ideas that we had for future work. So instead of considering pairs of states of this form, you could also consider like D-tuples. And well, it's not that hard to show that the homomorphisms that you get are just very similar to the ones we found for the case D is 2 for pairs of states. But you basically get a product of the fidelities of all the possible pairs in this tuple, all raised to some power z, which can be different for each pair. But it's very hard to prove DPI for these homomorphisms. So also if you were paying attention, you saw that we sometimes have to require this condition for some of our results to hold, that alpha I and beta I evaluates to 0 for some I, but in principle we could remove this condition But then we have to consider a slightly different semi-ring in which we find some homomorphisms, some additional homomorphisms that we're not sure of if they satisfy DPI. Yes, so yeah, I think, so the Vergleichsstandardsätze and similar theorems, I think they're very useful, and maybe there are many other possible results that can be derived from them. So often it's quite easy to define a new semi-ring and actually prove that it's all well defined, it's a real semi-ring. And then, but then identifying the monotone homomorphisms and derivations is just really hard. Sometimes you can identify them, but then it's really hard to know which ones satisfy monotonicity or not. Yeah, but I think there's still, yeah, some useful work that can be done with this. And yeah, that was it. And please have a look at our archive paper that was published last week.
Thank you very much. Are there questions?
Yeah, thanks for the talk. Can you say something more about this relative entropy you get at this limit set to infinity?
Yeah, so it looks like this right here, this one. Yeah. So yeah, I mean, you do need this specific prefactor that we put in front of it, else it will diverge. But yeah, so for any alpha, doesn't matter which alpha you take, you will get this for z goes to infinity. Okay.
More? Yes.
Thank you. So regarding your last comment, where in this case where the alpha I and beta I can be orthogonal for one I, so in this case, you know for a fact that it's not sufficient to have the order in the alpha z relative entropies?
So actually, we do think that it is sufficient. We do think that's our hunch, because okay, so we get actually extra. So it turns out that we need those homomorphisms or relative entropies, but also some additional ones that have the same form, but actually for alpha and z outside of the range where DPI holds. So that's outside of the range where DPI holds for general states. But we need to prove that DPI also does not hold for our specific states. And that's the issue. So,
Okay,
but we think.
But the condition would stay the same even with that condition.
Yeah, we think so. Yeah, I think so. Yeah.
Okay, thank you.
All right, more questions. So if I don't see any more questions, let us thank the speaker again.